Okay, so our first question asks us to simplify a radical. The radical they give us is the square root of n to the 13th power. Now, if you don't see an index, and an index is this little number that's in here in the crook of the radical, if you don't see a number, we always assume it's a 2. The square root is the most common, and that's the one you're going to assume it is. So even if it's not shown, we could write a 2 there if we wanted to. Now, whenever we're simplifying a radical, the easiest thing to do is to expand out the radicand. And the radicand is the stuff under the radical sign. So I can expand this out. N to the 13th power is just n 13 times, right? 8, 9, 10, 11, 12, 13. All right, now, so you want to expand it out. If it's a number, you would make a prime factor tree, but ours is this variable, so we're just going to expand it out. So now I'm going to look for groups of the same a variable or a number, and my group size is going to be my index. So this tells me my group size. In other words, I want to find 2 of a kind. So there's 2 of a kind, 2 of a kind, 2 of a kind. Let's just keep going. Now, anywhere that I have a group circled, one member comes out and the rest are thrown away. So underneath the radical, all I'm left with is an n. Everything else has been circled. And then in front of the radical, I have 1, 2, 3, 4, 5, 6. 6 n's, which could be written as n to the 6th. Now, when you're typing this into iMathAS, you have to be very careful. We're going to write n, and it tells you that right here at the underneath where it says note, but you're going to write n, and then you're going to put a space, and then you're going to put square root, which is SQRT, and then you're going to put parentheses, and then n. Oh, and I forgot, we should have had an n to the 6th. Let me add that. So n to the 6th will look like this. So that's n to the 6th square root n. And you can check over here in the preview. It shows you what it looks like. So you can see that's what I wanted it to look like. So we're fine. And let's look at the next one. So now this is not a square root, it's a cube root. And we know that, once again, because the index. And the index is this little teeny number here. So we're going to do the exact same thing we did before, but instead of groups of 2, now we're going to look for groups of 3. So I expand out my radicand using prime factorization if it's a number, or just expand the variables out. And I'm looking for groups of 3 of the same kind, sort of like playing cards. So I have 3 Ds here. I don't have 3Ds and another set of 3Ds. Those are just 2, so I can't circle them. When I have a group circled, one member comes out and the rest get thrown away. So I'm left with D cube root of D squared because I have 2 Ds underneath the radical. Okay? And if you're going to put this into iMathAS, you're going to say D and then a space. Oh, it's going to D in the space. Sorry, you're right. And then since it's going to be a cube root, we have to type in, and it says right here under the notes, root, and then 3, and then in another parentheses, we're going to write the radicand. There you go. And once again, they're going to show us this preview, so make sure it looks correct. Now, be very careful on this one, because this could be one you get right and you're just entering it incorrectly. So try it on a practice test until you're comfortable entering it into iMathAS. And if you have a problem, come see me. Let's try the next one. The next one says it's the 4th root of p to the 5th power. Notice the index, it's going to be 4. So we're going to look for groups of 4 of a kind. Okay, so we're looking for groups of 4 of the same kind, same number or variable. So this is p times p times p times p times p. So I'm looking for groups of 4. I circle it. One member comes out. All the other ones, sorry. all the other ones get thrown away. So I take one p out, and all the other members get thrown away, and I'm left with p to the fourth root of p. Let's practice entering that in the iMath AS2. So p. Now be very careful too. Notice I use a lowercase p. iMath AS cares. And then since it's not a square root, we have to say root, and then whatever the index is, 4, and then whatever your radicand is. So in our case, it was p. Okay. And we'll just check our answers. And I think we did it right, so we look great. Let's try the next problem. Okay, our next problem asks us to simplify some more. Okay. Now these have numbers with them, so they're not just plain old, the variables like the ones we had before. So let's clean this up. Okay, so I have the square root of 90c to the 15th. I'm going to do the same thing. I'm going to expand it out. Well, to expand out a number, I make a prime factor tree. And I end up with a prime factorization of 3 times 3 times 2 times 5. Okay, and I'd have 15 C's. So I'm just going to write them out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, now my group size is 2, and I know that because there is no index here. And I told you that if there's no index, we're going to assume it's a 2. So I'm looking for 2 of a kind. I have 2 3s, 2 C's. I have several of these 2 C's, right? So I'm going to go ahead and group them up. Okay, and so underneath the radical, I'm left with 2 times 5, which is 10, and then a C. Okay, and then outside the radical, every time I have a circle, I put one of its members outside. Okay, so I have 1, 2, 3, 4, 5, 6, 7 C's came out, and then 1 3. So I have 3 C to the 7th, and then the square root of 10C. So when you enter this, be very careful. 3 C to the 7th, put a space, and then if you want to use the square root, just put square root of 10C. We'll check that one. Looks good. Let's try the next one. All right, this one is a big number. So don't let this intimidate you. You can do this. Piece of cake. You guys have a calculator to help you for anything you get nervous on. Okay, so we have to find the prime factor tree for this giant number. We have a calculator. It's going to help us. Not a problem. So if I have 3, 5, 8, 4, well, I know I could try to divide by 2. That'd be the first thing I'd probably do because it ends in a 0, 2, 4, 6, or 8, right? So we know that is divisible by 2. So I'm going to say 2. And you guys have a calculator, so you could definitely go ahead and put that in your calculator, right? Go ahead and fix that. So I made the prime factor tree. So I went 2 times 1792, use my calculator if I need to. Then I divided this by 2, and I kept going, okay? So if I count this up, let's see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 2s, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I also have, let's see, a 7. And I have 5 B's. Okay, and now I'm going to look for groups of 4. And the reason I do 4 is because this little index is a 4. So I'm going to look for groups of 4. Here's a group of 4. Here's a group of 4. And here's a group of 4. 4 of the same kind. All right, so what's left underneath the radical? Well, 2 times 7 times b is 14b. Okay, now make sure you always bring over that little index, very important. It's the same index as 4. And then what came outside? Well, 1, 2 came outside, another 2, and then a b. So I'm left with 4b, and then the 4th root of 14b. Okay, so putting it in here, it'd be 4b, and then a space. And then since this is not a square root, I have to enter in root, and then whatever my root is, and then in another parentheses, whatever my radicand is. Oh, I think I left out the 14. Put that in. And then check to make sure it's the same. Okay? And we'll check our answer, and we got it right. One more. Let's try part C. This radicand is giant, 4, 6, 8, 7, 5. Okay, so this is where it really fails to look for the perfect square. Typically, people don't find it. So this is just a lot easier to do the method of just finding the prime factors. So to do the prime factorization, I start with a number. And then I look for 2 numbers that will multiply to be 4, 6, 8, 7, 5. Well, I tried 5 because I know it ends in a 5. So if I divide 4, 6, 8, 7, 5 by 5, I get 9, 3, 7, 5. And then I continue doing this. So I end up with 1, 2, 3, 4, 5, 6 5s. And then a 3. Okay? And it says I also have 6 J's. Okay, and that's all under my radicand and my radical to my radicand. So my group size is 5 because that's my index. So I'm going to look for 5 of a kind. So 1, 2, 3, 4, 5. I have 5 5s, and I have 1, 2, 3, 4, 5 J's, and I circle whatever I have 5 of a kind. Okay, that leaves me under my radical 15J. That wasn't circled. 5 times 3 times J. Everyone see that? Let me make sure. So for example, this and this was not circled. So 5 times 3 times J, that gives me the 15J. Okay. Now I'm going to make sure I do the same index. It always comes down. Okay. And then what was outside? Well, I have 1 5 and 1 J. The other members I just discard. So I'm left with, let's type this in, 5J and then a space and then root. Then I put the index, that's going to be 5. And then it's going to be the radicand, which is 15J. Okay, and I check to make sure it looks like my answer. It does. And I'll just check it and we're correct. All right, let's look at our next problem, number 3. Now, these are rational exponents. There's just a different way to write radicals, but we treat them the same as we do when we have integers as our exponents. So, for example, j to the 4/5 times j to the 1/6. Well, if I just had whole numbers, so if I had x cubed times x squared, what would I do? Well, that's the same thing as saying x times x times x, and this is x times x. So you can see that I add the exponents. So I'm going to do the same thing here. I'm just going to add the exponents. Okay? And you can do that several different ways. One way is you can find a common denominator. So a common denominator would be, I'm going to multiply the left one times 6 over 6, and the right one to 5 over 5, and I get 24/30 plus 5/30, which would be 29/30. Okay, so that would be j is 29/30. Okay, but if you're still struggling with fractions, let's get through this test. Another method is called the bow tie method. Some people use that still. So if you like this method, you'd say 4/5 plus 1/6. You multiply this direction, and then if it's adding, you add, and then you multiply this direction, and then you multiply for the denominator, the 2 denominators. And this is called the bow tie method. It works for simple fractions. So if you're still struggling with adding your fractions, maybe watch a video or two on that bow tie method. You can just Google it. Okay. And then one more method is you can use your calculator. So let's go ahead and work on that. You can check yourself with your calculator. So let's just try this. So if I were to enter 4 divided by 5, that's 4/5, right? Plus, let me go ahead and put parentheses around this so it knows it's 1 divided by 6. That's always safe. Okay, so let me go ahead and do that for all just to show you. I always put them around my rational expressions. So I'm just going to enter. All right, so I'm going to enter in my two fractions, and I'm going to hit enter. And it gives me a decimal, but I don't want a decimal, so I'm going to hit math, and then 1, and it gives it to me as a fraction. Okay, so you can use that calculator. It would be your friend too. So we have J 29/30. Okay, let's try the next one. This one here is a power. That's a power to a power. In other words, you get two exponents there. So let's just think what the rule looks like for whole numbers. If I have a whole number, if I had x cubed squared, well, if 2 is the exponent, whatever it can reach down and touch would be the base. So this is x cubed times x cubed, which we know is x to the 6th. So when you have a power raised to a power, you're going to multiply the exponents. We're going to do the exact same thing here. We're going to multiply 12 times 3/4. So if you haven't done fractions in a while and you need to review, one way you can do it is you can just multiply numerator times numerator. And then if we don't have a denominator, but we know it's over 1. So it'd be 36 over 4, which is 9. Okay? I can also use my calculator to help me. So here I go. So I'm going to say 12 times, and I always put fractions in parentheses. Good habit. And if it had given me a decimal, I would hit math 1, and it will give it to me back as a fraction. Okay? And our last one, we know the quotient rule says that when you have division, then you subtract the numerator minus the denominator. So for example, if you have x to the 6th over x cubed, you can subtract 6 minus 3. It's a shortcut to get the answer. So we're going to do the same thing here. We're going to say s to the 3/6 minus 33/6. Okay, well, these are nice because they have the same denominator. So I can just say 3 minus 33 is going to be negative 30 over 6. We keep the denominator the same, which is going to be s negative 5. Okay. And typically, iMath AS likes us to write in positive exponents. So I'm going to make that be 1 over s to the 5th. Because we know that the rule for exponents says that if you want to make a negative exponent positive, you change its location in the fraction. So in this case, it's in the numerator because it's over 1, basically, right? And so we're going to move in the denominator. So this would be my answer. Okay? And let's just check those out. Looks good. Okay. Number 4. Number 4 are radicals, and they ask us to add them. Now, one of the themes in this class I keep trying to nag you guys about is that we only add like things. We only subtract like things, whether it be like terms or like denominators, or in this case, like radicals. So we only want to add like radicals. And to be a like radical, you have to have the same index and the same radicand. That makes you a like radical. So if you do have the same index and the same radicand, then if you have a number in the front, a coefficient, you just add the numbers in the front, and then you keep the like part the same. That's a common theme, that we keep the like part the same. Okay? So let's just check ours out. The only thing tricky on these is you have to make sure before you judge them as like or not like, you have to make sure they're simplified. So let's try 8 square root of 245 x squared. All right, so it's a square root, so I have to see, can I simplify it first? So 245, if I use my factor tree, that'd be 5. And if I put that in there, that's going to be, let me do that quickly in my head. That's going to be 49, and then I'm going to say 7 and 7. So my prime factorization is 5 times 7 times 7, and I'll expand out x squared as x times x. Now don't forget there's an 8 already on the front that's a coefficient. So my group size is 2 because I don't have one. If it's not one shown, we know it's 2. So I'm looking for groups of 2. Well, I have 2 7s and two x's. So every time I have something circled, I take one member out and I put it in the front. So on the outside, I have 56x, and then underneath the radical, I still have a 5. Okay, so let's put that down here. That's my first radical that I've just gone ahead and simplified. Let's try the next fraction, the next radical. Okay, the next radical says 10x squared to 80. So I can make that little tree again and say that's 8 times 10. And then I could say 2 times 4. And I'm going to be left with 4 2s and a 5. Okay. My grouping size, once again, is a 2 because I don't have any group size. I know it's a 2. So every time I circle a group, one member comes out of the factor in the front. So I'm left with 2 times 2, which is 4, times 10 is 40x square root of 5. So let's put him down here. We have one more radical that we need to simplify. This one here, oh, I'm sorry, was a minus. So let's make that be a minus coming up. So it is a 45x squared. So 45 is 9 times 5, which is 3 times 3. So my prime factorization is 3 times 3 times 5. 3 times 3 times 5. And then I expand out my x squared as x times x. My group, once again, is a 2. The reason it's a 2 is because I don't see anything. If there's nothing specified, it's a 2. So I look for groups of 2 of a kind. I have 2 3s, so one member comes out, and one member of the x's comes out. The other member gets thrown away, and I'm left with 3x square root of 5. Okay, so far we're down to here, okay? Let's move this a little up here. Now, I'm not done yet though, because now I know I have like radicals. Remember, like radicals, get a different color here, yellow. They're like because this is the same. Okay? Just like anything like, when we have like terms or like fractions, we keep the like part the same and we add or subtract the coefficients. We're going to do the same thing here. We're going to keep the like part the same. It's a 5, square root of 5. And all I need to do is, what is 56 plus 40? That's 96. Minus 3 is 93x. And that's my answer. Let's type that in. So it's going to be 93x, put a space, and then write square root, and then write 5. Okay, and always check your preview. Make sure that it looks correct. Okay?